Theovis, the idea made visual. The number E, about 2.718, shows up in the strangest variety of places: cooling coffee, radioactive atoms, bank interest, population growth, AC circuits, even quantum mechanics.
That's what's always bugged me. What could a decaying atom and a savings account possibly have in common with that one specific number?
By the end, you'll see they share a single sentence, and E is just the natural language for saying it. Forget the decimal for a moment. The function e to the x is defined by one astonishing property. Its slope at every point equals its own height.
Wait, the steepness of the curve is the same as how high it is? Everywhere at once?
Everywhere. That single fact is the seed the whole forest grows from. Watch the point ride the curve. At each spot, the little tangent line's steepness is exactly the height of the curve there. Low and shallow, high and steep.
So as it gets taller, it automatically gets faster, which makes it taller still. It's feeding on itself.
That runaway feedback is the signature of exponential growth. In symbols, the derivative of e to the x is e to the x. It's the one function calculus hands back completely unchanged.
No other function does that so cleanly? That's why it must be special.
Here's a peek under the hood. Write e to the x as this infinite sum. Differentiate it term by term, and each piece simply becomes the term before it, so the whole sum reproduces itself perfectly.
So the self-derivative property isn't magic at all. It's baked into the series. Every term hands its slope down to the next one. Elegant.
Here's the universal pattern. Whenever a quantity changes at a rate proportional to how much you already have, you get this equation, and its solution is always an exponential.
So the more there is, the faster it changes. Written as a formula, forces E to appear. That's the bridge.
Picture a dish of bacteria, where each cell splits on a steady schedule. Twice as many cells means twice as many splits per minute. Rate proportional to amount. Exactly our law.
So the population rockets up in exponential, and just knowing the doubling time pins down the entire future curve.
And that pattern is staggeringly common. More money earns more interest. More radioactive atoms means more decays each second. Hotter coffee sheds heat faster.
More rabbits make more rabbits. So every one of these is secretly the same differential equation, just with a different name on the quantity.
Newton noticed it in cooling. A hot object loses heat at a rate proportional to how much hotter it is than the room. Big gap, fast cooling. Small gap, slow.
So the temperature difference decays exponentially, which is exactly why coffee cools quickly at first, then crawls the last few degrees toward room temperature.
Now make the proportionality negative. The more you have, the faster you lose it. The exact same law runs in reverse: smooth exponential decay.
So growth and decay aren't two phenomena. They're one law with a plus or minus sign. Cooling coffee is just a savings account running backwards.
Proportional change leaves a tell. Growth has a fixed doubling time. Decay has a fixed half-life. The time to double or to halve never changes, no matter where you start.
That's why carbon dating works. The half-life is rock steady. The exponential's rhythm is always the same.
There's a time scale the process itself prefers. The e-folding time. How long until a quantity grows by a factor of e, or decays to about 37% of where it started?
So instead of doubling, you can measure in factors of e. The exponential brings its own natural unit of time.
But where does 2.718 actually come from? Imagine 100% interest. Paid once, your money doubles. Paid in smaller, more frequent installments, you earn a little interest on your interest.
And if you compound it infinitely often, continuously, that snowball settles on exactly e. So e is what growing as smoothly as possible converges to.
You can almost watch it converge. Compound once a year, and growth is a jagged step. Monthly, then daily, then every instant. The steps shrink until the staircase melts into one smooth exponential curve.
So the exponential is the limit of infinitely many, infinitely small growth steps. Continuous change is just discrete change pushed to its extreme.
Numbers make it real. $1,000 at 5% compounded continuously for 10 years is 1,000 times e to the 0.5.
E to the 0.5 is about 1.65, so it grows to $1,648. The exponent is just rate times time.
And decay is the same law backwards. Carbon-14 halves every 5,730 years. After 2 half-lives, about 11,000 years.
You're down to a half of a half, just 1/4 left. That steady halving is exactly how we date ancient bones and wood.
So E isn't an arbitrary constant someone chose. It's the inevitable result of growth that never pauses to compound. Growth happening at every instant.
Continuous proportional change has a native number, and that number is E. It was waiting there all along.
You could use base 2 or base 10, but watch what happens. Their derivatives pick up an ugly extra factor, the natural log of the base. Only for base E does that factor become exactly 1.
So E is the unique base that makes calculus clean? The only one whose growth rate isn't scaled by some leftover constant?
E brings a twin, the natural logarithm. Remarkably, the area under the simple curve 1 over t is exactly the natural log, the function that undoes e to the x.
So east and ln are a matched pair. One turns a rate into an amount, the other recovers the time it took. Two sides of the same coin.
Here's where it gets beautiful. We've fed in real growth rates. But what happens if we feed it an imaginary rate? Multiply the exponent by I.
I have no idea what growing at an imaginary rate even means. How do you grow sideways into the imaginary direction?
This is the answer. Pushing in the imaginary direction doesn't make a number bigger, it turns it. An imaginary growth rate is pure rotation, steady turning around the origin.
So real exponents stretch and imaginary exponents spin. Growth and rotation are the same machine, just pointed in different directions.
That rotation is Euler's famous formula. e to the I theta equals cosine plus I sine. The exponential of an imaginary angle is a point walking around the unit circle.
So, sine and cosine, the shapes of every wave, are hiding inside the exponential? That's how E sneaks into oscillation.
One special case is often called the most beautiful equation in mathematics. Turn the spinning exponential exactly halfway around the circle, angle pi, and you land on -1. So e to the I pi plus 1 equals 0.
5 of the deepest constants, E, I, pi, 1, and 0, in a single line. And now I see why it's true. It's just half a rotation.
Every oscillation, a vibrating string, an alternating current, a swinging pendulum, is the shadow of something turning. And turning is what E does with an imaginary rate.
So that's the unification. Decay is E with a real rate. Waves are E with an imaginary rate. Same function, 2 flavors of exponent.
And you can have both at once. Give E a complex rate, a real part and an imaginary part, and it spirals, shrinking as it turns. Its shadow is a damped oscillation, dying away as it wiggles.
That's a plucked guitar string, or a child's swing coasting to rest. One complex exponential captures the whole thing, the fading and the wobbling together.
One function, e to the complex rate, holds growth, decay, and oscillation all in a single object. Here's the deeper reason E is unavoidable. Most of physics is linear differential equations, and the exponential is the one shape that differentiation barely touches. It comes back as itself times a number.
So when you guess a solution to a vibration or a circuit, you guess an exponential, because nothing else stays in one piece under all those derivatives.
Let's make that precise. Differentiating an exponential just multiplies it by a constant, lambda. The shape is untouched. In linear algebra language, exponentials are the eigenfunctions of the derivative.
So differentiation, which scrambles most functions, treats exponentials as fixed directions. It merely scales. That's the perfect lead-in to the next episode.
So it pours into everything. A shock absorber is a decaying exponential times a cosine. Electrical engineers run all of AC theory on complex exponentials, called phasors.
And a quantum state literally evolves as e to the minus I energy time. Rotation in the abstract. The same idea all the way down to atoms.
One more haunt. The normal distribution, the bell curve behind averages and errors everywhere, is built from e to the minus x squared. Even randomness leans on it.
So, from atoms to averages, the moment something changes in proportion to itself, or curves, or oscillates, E shows up. It's relentless. Let me say it back. E is the function equal to its own slope. That makes it the answer whenever change is proportional to amount, growth, decay, and with an imaginary rate, rotation and waves.
Exactly. E isn't everywhere by coincidence. It's everywhere because rate proportional to amount is everywhere. And E is simply what that sentence sounds like in mathematics. If you want the history and the deeper theory, these trace from Euler's hand to the differential equations that run modern physics. We just saw exponentials survive differentiation. Next time, we'll see that this makes them the natural coordinate system, the eigenvectors, of every linear system.
From E to eigenvectors. See you there.
If it finally clicked, subscribe. It really helps. And I'll see you in the next one.